Welcome everyone to the final recording for the JetBlue case. In this recording we are going to expand our analysis of JetBlue hedging with forward contracts to a more sophisticated backtesting of this strategy. In our previous discussion we considered only a low jet fuel price and a high jet fuel price, and that was associated with a low oil price and a high oil price. But suppose that you were the Chief Financial Officer of JetBlue and you said, I don't think that's sufficient. I would like you to test your hedging approach whereby you enter into futures contracts for 20 million gallons, to hedge the equivalent of 20 million gallons of jet fuel using, in our example, about 500,000 barrels of oil futures. Suppose the Chief Financial Officer says, test this many times. Well, one way you can perform an analysis many times is to look at some historical data. So what we're going to do is consider the following situation. Helena Morales is going to be the Chief Financial Officer for JetBlue. She wants to backtest a WTI hedge. She takes a monthly hedge position of 20 million gallons for 2012. And we're going to ignore volume risk. So we're going to assume that there's no uncertainty about how many gallons of jet fuel JetBlue is going to consume in any given month. And we're going to ask ourselves, well, what would have been the outcome for JetBlue if it had entered into the same hedging strategy that we analysed just once in the previous presentation. But we're going to analyse that strategy 60 times for 60 months worth of data from 2007 to 2011. And what we're going to do is consider what would have been the monthly jet fuel costs inclusive of any payout under the futures contract under two scenarios, without a hedge and with a hedge using WTI oil futures contracts. What we're going to do in this analysis is to assume that the strike price in the futures contract is the spot price of WTI oil at the end of the prior month. For example, at the end of December 2006, we have a spot price for WTI oil of $60.85 per barrel. We're going to assume that that is going to be the strike price for a WTI oil futures contract in that month. We are going to run our regression analysis using the 5 prior years of data on a monthly basis, just like we did earlier, but we're going to roll that window forward 1 month at a time. So for example, we're going to start with 5 years of data from January 2002 to December 2006 to estimate the number of forward contracts that we need in January 2007. Then for February 2007, that window is going to roll forward 1 month to February 2002 to January 2007. We're going to do that over and over again. So for example, in that regression, where the historical data set is January 2002 to December 2006, we would have the regression outcome of the percentage change in jet fuel price equals 1.07 times the percentage change in the WTI price. That figure of 1.07 is different to the 0.81 figure that we had in our previous analysis. We're going to use the same equation that we used before to estimate the number of futures contracts to use for hedging purposes. We're going to say that the number of contracts to be bought by JetBlue is going to be 20 million gallons of jet fuel times the hedge ratio from the regression equation, remember having constrained the intercept to be 0, times the $1.736 jet fuel price per gallon in January 2007, divided by the strike price for WTI oil futures, which we're going to assume as a proxy is $60.85. That's going to give us 610,303 futures contracts for hedging purposes. That can be contrasted with a figure of just under 500,000 that we had in our previous example. To do this analysis, I'm going to turn to our spreadsheet. I'm going to show you a couple of equations, a couple of functions in Excel, which are going to be really useful. So previously, we computed or compiled a scatter plot. And in that scatter plot that you can see in chart 1, we have a line of best fit. That slope of that line of best fit is a hedge ratio, and that hedge ratio allowed us to work out the number of futures contracts. But if we were going to do this analysis 60 times in that rolling window, we don't want to produce 60 scatter plots and then write down the answer every time. That's going to be very time consuming. We want to be able to link the outcome to some computation. Another reason we want to link the outcome to our computations is that we think that 5 years of monthly data is a reasonable window to estimate the hedge ratio. But what happens if we change our mind? On Monday we think 5 years of monthly data is a reasonable sample period. What if on Tuesday someone in our organisation says, you know, I'd really like to see the analysis using 6 years of monthly data. Can you redo the numbers? Well, we just want to change the inputs into some function in Excel and then automate the output. That's going to save us some time. So let's look at a couple of functions in Excel. Now, a very simple way to estimate the outcome from regression is via the intercept, the slope, and the r-squared functions within Excel. These functions aren't going to allow us to constrain the intercept to be 0, so we're going to do something else for that constraint. But I'm just going to show these basic functions for future reference. They're really handy. So if I wanted to estimate the regression output for our equation, let me write down the equation first so we know what we're talking about. We're going to have the percentage change in jet fuel price equals intercept plus slope times the percentage change in the WTI oil price. So the percentage change in the jet fuel price is going to be my dependent variable. The percentage change in the WTI oil price is going to be my independent variable. And I'm going to come up with some functions to estimate the intercept, the slope, and the r-squared, which will tell me the proportion of the month-to-month fluctuation in the jet fuel price, which can be explained by the month-to-month fluctuation in the WTI oil price. So here's our functions. For the intercept, I'm going to write equals intercept. I'm going to open parentheses. I'm going to highlight the y variables, that's the dependent variables, the percentage change in the jet fuel price. Then I'm going to put in a comma, and then I'm going to highlight the cells that have the x variables, the percentage change in the WTI oil price. So I'm going to go to my data page. I'm going to highlight column J, and I'm going to grab cells J213 to J272. That's going to give me 60 cells for the 60 months from January 2007 to December 2011. Then I'm going to put in a comma, and I'm going to highlight cells I213 to I272, and I'm going to close parentheses. And if I hit enter, you'll see that the intercept is 0.23%. I'm going to lock in the row and the column by putting dollar signs in front of 213 and 272 and in front of I and J. And then I'm just going to copy and paste that formula into the cell below. And I'm going to change the word intercept to be slope. So I'm going to refer to the same array, the same cells in the data, but I'm just going to change the word intercept to slope. If I write slope, you're going to see the figure of 0.81, which is going to be very close to the slope we estimated before. It's not quite the same because we haven't constrained the intercept to be 0, but it's pretty close to the slope we had before. If I copy and paste that formula again and change the word slope to be RSQ for R squared, that's going to give me an R squared of 78.72%, which tells me that 79% of the fluctuation in the jet fuel price from one month to the next is associated with a percentage change in the WTI oil price. That means there's 21% of the movement in the jet fuel price from one month to the next, which is something industry specific. It's not to do with overall oil prices. Well, that's fine as far as it goes, but we want to have a more precise hedge ratio because we want to constrain the intercept to be 0. Now to do that, there isn't a pre-packaged function in Excel, but there is something called an array function. And to enter an array function, we just have to be a little bit careful about how we enter it. When you have an array function, you're going to highlight many cells at once, not just one cell. And we're going to produce output for many cells. And the array function that we're going to use is called linest, spelled L-I-N-E-S-T. That's going to be the function. And so I'm going to, within these pink cells here, highlight all of those cells. I'm going to put in my function, and I'm going to finish by hitting Control-Shift-Enter to enter an array function into all of these cells. Now what that means is that you can't change the function in just one part of that array. You can either change all of the information in that box, the array, or you can change none of it, but you can't change individual cells within that array. So pay very careful attention to the way we enter an array function. I'm going to highlight all of the cells first, then I'm going to go to my formula bar and I'm going to write equals L-I-N-E-S-T. I'm going to open parentheses. Now again, this looks similar to what I just did. I'm going to highlight the Y's and the X's, that is the dependent variable and the independent variable, and then I'm going to add in some other useful inputs to give me more information. So I'm going to highlight the information from the discrete change in the jet fuel price. I'm going to go from J213 to J272. I'm going to put in a comma, and then I'm going to put in information for the independent variables, going from I213 to I272. Then I'm going to enter some other information. I'm going to put in a comma, and I'm going to decide, do I want the intercept, also called the constant, to be set to be 0, or do I want it calculated in the normal manner that is unconstrained like I did 5 minutes ago? I'm going to enter 0, so I'm going to constrain the intercept to be equal to 0. Then I'm going to put in another column, and the formula is asking me, do I want to have some additional regression statistics here? Things like standard errors and R-squared that people use to make interpretations of how much potential estimation error there is in the sample of data. Another word for that is people use that information for testing of statistical significance, in which they're trying to work out, could I have observed a result from this regression analysis just by chance, because this sample could have been affected by some unusual events happening in that particular time period. I'm going to hit 1 to produce some statistics. I'm going to close parentheses, but before I finish, I'm not just going to hit enter, I'm going to hit Control, Shift, Enter. I'm going to hold down the keys as I do it, because that's going to populate the entire array. So if I hit Control, Shift, Enter, I've populated the entire array. And you can see in that formula bar, there are these, I don't know the name of those, they're sort of curvy, unusual looking brackets or parentheses. That means I've populated the entire array. So to interpret this information, I have a slope of 0.81 and an intercept which is 0. Remember, we constrained that. And that's identical to the outcome we had from our scatter plot. You see how we've got a 0 intercept and a slope of 0.81? Same output. We have an R-squared of 79%. We have a standard error of the slope of 0.054. That means approximately the true relationship between the percentage change in jet fuel price and the percentage change in the WTI oil price in the population probably lies somewhere between 0.7 and 0.9. All right, that tells me that 2 standard errors either side of the slope probably captures what is truly the relationship between those variables in the entire population as a rough approximation. And there's some other information that we're not particularly concerned about right now, but they're the highlights. Now, the reason that function is relevant is because in this analysis that the Chief Financial Officer wants, she wants to see this analysis performed over and over again. So I can use my linest array in order to repeat the analysis over and over again, but with just different cell references. So instead of referring to rows 213 to 272, I could refer to rows 212 to 271 or 211 to 270 and do that over and over again. And that's what I've done in one of these data sheets. In the data page here, if I refer to one of these cells, here's my hedge ratio in column K. I'm using the lin-est function, but I've only grabbed one cell. You see on the reg output page, I grabbed all of these 10 cells to begin with. If I just grab that first cell in the top left-hand corner, I'm just going to grab the slope, and that's the only information that I need to do this analysis. So in this data sheet, what you can see is that I've produced the lin-est array function over and over again, and I'm not asking for any additional output. So I just have a column where I'm grabbing the hedge ratio over and over again using the prior 60 months worth of data. That hedge ratio is flowing through to the number of contracts that I'm going to use for hedging, and that information is flowing through to computations of the unhedged energy cost, the payoff from hedging, and therefore the total cost associated with hedging using WTI futures contracts. Now, we're not going to do just an Excel class. You can look at those computations on your own if you choose. I want to be able to interpret the output. So what I've done in the PowerPoint presentation is summarize the output on these couple of slides. So the first thing to note is that the average energy cost from being unhedged and the average energy cost from being hedged is about the same, which is what we expected. Nobody here is forecasting oil prices. Nobody here is strategically buying oil when we think it's low and selling oil when we think it's high. So on average, we should be in about the same position being hedged or unhedged, but it should reduce our risk associated with purchases. Now, it turns out that in this particular example, you've got about the same volatility of aggregate energy cost, including hedge payoff, from being hedged or unhedged. But that is just because oil prices were very volatile during this whole time period. That doesn't really tell us how much risk there is for JetBlue. The correct way to interpret JetBlue's risk is to look at the difference between its energy cost in any given month to compare to what it would have expected to pay at the start of that month. And that I can summarize with the following diagram. If you look at this very volatile, bright red line, that represents the difference between the actual energy cost in a month versus what JetBlue would have anticipated the energy cost to be at the start of that month, based upon jet fuel prices at the start of the month. So you see this massive fluctuation in actual jet fuel costs versus what was expected. What happened is that jet fuel prices skyrocketed during a short period of time and then collapsed after that. So you see a very volatile stream of difference between actual energy cost versus what JetBlue expected. Whereas if you look at the dark red line in the graph, what you see is the actual energy cost minus what was expected if JetBlue had hedged every single month over and over again. And you can see that that dark red line is a lot less volatile. And that means that JetBlue's energy costs are much more predictable from one month to the next. And if your energy costs are more predictable, when JetBlue is selling tickets, it can price the tickets at an appropriate margin above its cost. And that's the information that's important for JetBlue. Remember that JetBlue has the underlying risk because of its business model. It is selling tickets to customers at a fixed price before it knows what its actual costs are going to be in any given month. If JetBlue has more predictability of costs, it can price the tickets at a margin above those costs. That will allow JetBlue to take on more debt and therefore have more tax benefits, or at least hold less cash in the business and return the cash to shareholders, which makes it more productive. If you look at this outcome on a rolling 12-month basis, you can see the difference between the actual and the predicted energy costs 1 month in advance, cumulated over a 12-month period. And you can see that from over different 12-month periods, you could end up with aggregate energy costs, which are very different to what was expected on a 12-month basis. And remember, JetBlue is selling tickets for up to 12 months. So that 12-month window is very important. Whereas if you look at the difference between actual and expected energy costs from being hedged over and over again in the dark red line, you can see that line is much less volatile. To summarize, the standard deviation, that's a metric of dispersion, of actual versus expected energy costs 1 month ahead from being unhedged is about $4.6 million. But with hedging, that volatility is reduced to less than half. It ends up being about $2 million. All right, that's about 40 to 45% of the risk exposure from being unhedged. And that could be highly beneficial to JetBlue. Now, if you were doing this for real for JetBlue, you wouldn't just look at hedging 1 month ahead. You would have a profile of hedging, which is probably hedging lots of fuel cost exposure 1 month ahead and very little fuel cost exposure 12 months ahead. Because over that 12-month period, you can be adjusting the pricing as actual information for energy costs comes through. But you want to be hedging your exposure to a great degree in the short term, because you want to offset the potential short term for financial distress. Ladies and gentlemen, that is the end of our discussion of JetBlue. There will be some quiz questions associated with hedging of commodities. I will look forward to your attempts at those questions and the discussion, any comments you have or feedback or questions you have for me in the coming days and weeks. Thank you very much.